This video is a part of my full digital guitar pedal course. In this episode, I'm going to introduce you to the world of DSP and how to make a simple, soft, and hard clipping distortion that sounds like this. This course is also sponsored by PCBWay, a quick, cheap, and well-made solution for getting PCBs custom manufactured. I'll show you how to order through them later in the course, so stay tuned for that. All right, so here we are back in the code. I'm just going to kind of explain what all of this is and how the Daisy code is kind of set up and works. I'm going to assume you have some general knowledge, like you know what a variable is and maybe a for loop or if statements. I'll kind of still go over stuff loosely so you don't have to be super knowledgeable, but I assume that you've watched some videos and are at least somewhat acquainted with any programming language. Maybe you've touched something like Python or does some like web development or something in JavaScript. So I'll kind of explain some of the more C++ things that are specific to here, but there's honestly not much at all, at least for what we'll be doing for this. You can see here we have like your include. So this is just including the Daisy seed and some helpful things they have for that. And then the Daisy SP library, which is that library I mentioned that's just full of all these helpful DSP things and that we'll definitely be touching later to do our chorus effect. This using namespace is nice. It just kind of shortens how much we have to type. So it's a good thing to say. And then I'm also going to do using namespace Daisy seed. Oops. Since we're going to be using the Daisy seed. So there's just a few things there that'll be nice to have that written out for. And then this is where we actually declare the Daisy. This hardware variable is going to be, as you see, where we like initialize and do all that. So starting off, here is the audio callback function. This is just where all of the processing is done. I'll explain more about kind of digital audio in a second, how that works. But then here is your main function, which just runs right when you boot up, the Daisy. So that's why we have like initializing and setting sample rate and everything is in here. But yeah, the audio callback here, you can see we have our inputs and output buffers, which will hold, they're basically arrays of all of the incoming and then the outgoing numbers, and then we have size here. This is a for loop, which is looping over all of the incoming data from whatever we plug in, and then we can take those samples and do stuff to them. So I feel like we do need some sort of understanding of digital audio and what exactly is coming in to us and what our data is. So you can see here, this is how our block size is set. It defaults to 4, and this is the number of samples that will be handled in our callback. If I assume you've used DAWs and stuff, so that's like your buffer size, which you might be thinking, like in a DAW, you are typically like 256, 512. Sometimes you're going all the way up to 5,000 and something. But in a DAW, we'll obviously be running so many more effects and also just your computer's running your whole operating system and everything. So buffer size like 4 would be way too intensive, whereas the Daisy is just running this simple code here. So 4 is totally fine. If you are finding that your pedal is glitching around or something, then that is a value you could play around with. But that just basically is saying how big these buffers are going to be in this audio callback. But it's not something you really have to worry about, because as you see here, the first thing that they do is give you a for loop, which is just a way to loop through something, typically like an array or a list or whatever, which is what the buffer is. So it's just looping through it, making sure it's the size, which the audio callback handles. And that's going to be 4, but it's just said right there. And then we can just apply all of our processing to each individual sample. But you can always just kind of think about it in these single little numbers instead of like the overall signal. Even when we deal with delays and everything, those are still just kind of referring to the current one and then maybe the one before it or something. So you can really kind of just ignore the for loop and now just be inside of it and do all your processing there. To just understand what this is saying, your output buffer, if that's just a variable that if you set it, it's going to be how your output sounds like. So here you can just say it's saying the output at channel 0, which this corresponds to that pinout chart. So if I bring this back, you can see out 0. So that's just if you're plugged in there, that's going to send to there. If that's at out 1, which the right below it does, and that's going to be the other one. This just does both. I'm only hooked into 0, so I can just delete this if I wanted to. I is just saying which sample within that input buffer we are going, or the output in this case, that we want to change, and then that will be mirrored in input, which is also that same channel, and then which sample it is. So that'll probably be a number between 0 and 3 since our block size is 4, but that doesn't really matter. We just can say I, because then we could change this to 128 or whatever, and it'll still function exactly the same. So the first thing I want to do is just code a really simple distortion, just a hard clipping digital distortion. That's probably not going to sound great, but it doesn't really matter because I think it's a great kind of way to just get your head understanding how DSP works before you start doing more time-based effects, which are definitely much more complex. So dealing with delays, reverbs, filters, and everything. With DaisySP, we won't really have to worry about that, but I think since DaisySP, we'll just kind of be able to simply throw a chorus on. I think coding a distortion from scratch is both very simple and then nice to not have to rely on another thing. So to do a distortion, I mean, you can think of a distortion in your DAW or other guitar pedals you have and how that works. You might be familiar with the terms hard clipping and soft clipping. I'm not going to get into it that much, but hard clipping is just once you're above this certain threshold, just hard cut and say, no, we want it to be back down to here, whereas soft clipping has more smoothing. It's kind of in digital world used to replicate old analog stuff that will naturally have soft clipping because hard clipping can't really be a thing in the analog world. But we're going to do hard clipping because it's simple to program. And how that works is essentially you just take your audio, you amplify it a ton, and then you hard clip and you say, go back to a normal range. And then that just distorts it. It clips, like in your DAW when you just are going above, and then you limit it, and now it's still distorted, but you're not blowing your ears out. So you can think of our input signal coming into the pedal, into our input buffer. It's a very complex signal, obviously, but just think of it as like a sine wave. In the Daisy here and most kind of software digital things, when you're coding, the range will be from -1 to 1. And in our sine wave, according to the sample rate and everything, there'll be all these discrete points along it that we're sampling at. And those are just numbers. Those are just numbers being fed into this buffer that we can mangle. Like we said, a distortion, all we are doing is amplifying. So if all those numbers are just showing amplitude, then to amplify it, we just need to multiply them by a certain number, let's say 10. So we're multiplying now every single sample by 10, and then we want to hard clip it. So we do that by saying just if this sample is above 1, which was like our base range, or below -1, just put it back to 1 or -1. And that's literally it in terms of a simple distortion. It's not going to sound great, but then we can determine the amount of distortion that we'd like by that gain thing so that we can map that to a knob. So coming back into the code, if you've coded before, I hope that this is something that you could maybe try and do on your own and figure that out. If not, it might still be a little bit daunting, and that's totally fine. But yeah, first let's just declare our distortion variable. So I can say float distortion amount, and let's just set it to 0. So then down here, since this is just simply putting input into output, if we want to do all this processing, we don't want to just be throwing it into output every single time. So instead we can create a new variable that's just locally in the callback function. Let's just call it wet signal or maybe distorted signal. For now, and then here I can say distorted signal equals, and then like we said, all we want to do is amplify it or multiply it, so I can just take that times distortion amount. And actually the default here we should actually put to 1, because obviously if we times it by 0, it'll be completely silent. So default, we'll just set it to 1. Distortion amount. So in pseudocode, as I explained earlier, we say if it's above 1 or if it's below -1, then set it to 1 or set it to -1. And luckily, that's not really even pseudocode. That's pretty much just exactly how we code it. So I'm just going to say if distorted signal is greater than 1, then distorted signal equals 1. And then we could say else if distorted signal is less than -1, distorted signal equals -1. And that's it. Then we just have to go and take our distorted signal and feed that into the output. So I'll take out, get our channel, which is 0, get which index we're at, which is I, and then say equals distorted signal. So before I flash this on, first off, we need an actual distortion amount. But I also just want to say, when you're dealing with audio like this, really be careful when you go to listen back and play stuff, because say I put this to 100 and then maybe I did not write this, or I commented it out accidentally or something, or forgot to uncomment it. then that signal is going to be 100 times louder, which could destroy your speakers or destroy your ears, more importantly. So always in a second when we'll turn this on, make sure your gain starts down on your interface, or your headphones are down, or you play it in speakers ideally when you first start. I trust that this will work because that's exactly what the code does, but never trust it. Don't be too overconfident, because then that's when you mess stuff up. So for now, I'm just going to set distortion amount to like 10 probably is fine, and then flash this code on. So make sure you reset boot and then put it on. All right, I did end up switching to my Daisy pod just because the headers on this were being really annoying in the breadboard, because they got to be filed down or something. They're really thick, so they kept popping out. But I got the pod here, and let's hear this distortion. So if I just turn this up, it's probably gonna get really loud. But we got distortion. Probably sound a lot better on a guitar, but I just have so much set up here that it'd be really annoying for me to do. But I do just want to show you how even just this simple hard clipping distortion and the knowledge we gained can be easily then put onto other things. Like if I were to search DSP soft clipping equation, and then I'll do the first one here. Like you could see this, and to some people, I mean, if you haven't like done math in a while, it might be kind of complicated, but when you really read this, it's saying when x is less than or equal to -1, make it -2/3. When x is in between -1 and 1, make it x minus x cubed divided by 3. And then when x is greater than or equal to 1, make it 2/3. And I mean, that's nearly code language. So we can say when x is greater than, and then this says or equal to, then we do 2/3, right? So I can just do, I could actually write that out, or you could write 0.66, it doesn't really matter. And then when it is less than or equal to, we want to set it to 2/3. And then I can just say else, because if it is not between those, then we know it is going to be in the middle. And then remember, x in this case is just this distorted signal, because x is your input, and right before this we set our input to this. I could just say distorted signal equals distorted signal minus, and then I could do parentheses here. We just want to cube the distorted signal, so I could literally just write out distorted signal times distorted signal times distorted signal. And then we want to take all of that, so we have to put it in parentheses, and then we can divide that by 3. I did forget a negative here, so make sure to put that. And I would change your distortion amount down a bit. This is something you can play with, especially if you have a guitar lying around. Soft clipping would be good for not as much distortion as I was just throwing into the hard clipping, so yeah. Hard to hear the difference with the drums I have, but maybe you can if you're playing around with it. But yeah, this is a great way to just kind of get really familiar with how DSP works and things, is simple distortions. I think they're a great beginner point. You could see like here's somebody, I don't know if they're asking for help, but yeah, like here's another thing that you can implement, and it's just a ton of if statements. And they're kind of doing this differently. Instead of applying a ton of gain, they're putting the threshold in which they start compressing. That's what you change. So it's interesting. You can kind of just play around with that. Okay, but staying with this code, or the hard clipping one, it doesn't, I mean, do which one you want. Obviously distortion amount, great, but we would want to control that, right? So we should use that knob that you might have hooked up earlier. So to get that actual signal from the knob, on the Daisy documentation, they have this section here in tutorials. If you hit ADC inputs, this is a really great resource for this. It's pretty much exactly what I'm about to teach you. So if you want to learn more, you can kind of read through this whole thing. But yeah, we essentially are going to be declaring this ADC channel config. But before we do that, it's a great thing to just get our kind of the pins that we have connected all of our knobs to, and actually just fully define them. So in C++, you can do this define keyword here at the top using a hash symbol, and then we can just say define pot 1, and then whatever that ADC pinout value that it was, you just write A and then whatever number it was. So you don't have to write DC or anything, but if you hooked it up to ADC0, you just type A0. This will throw an error if you didn't do this daisy seed namespace, so definitely do that. For me, like I said, I'm using the pod, and While they do have, when you declare your new project, you could say that the board is for the pod, and there's some really great kind of easier ways to declare the knobs. But since we're going to be making our own pedal in the future, I'm just going to treat it as if we're on the seed. So I'm going to the actual pinout here and seeing which ones they have it hooked it up to, which it seems that pot 1 and 2 are A6 and A0. So I'm going to just declare that. So just write every single pot that you ended up hooking up. I'm going to do pot 1. I think this one they called A0, and then this was A6, and you can just do the same. So now if you only have one knob hooked up, there is a, using the ADC channel config, it's really easy to just initialize a single one, but I'm going to treat it as if you have multiple, as I do, and since we will in the future, you actually don't need semicolons here. But yeah, so as you can see here, they have this really nice kind of tip of naming your ADC channels using an enumerator, which is just a C++ thing or many coding languages that we can write out all of our knobs, and those will all just technically be integers behind the scenes. So I could say enum ADC channel, and then depending on how many knobs you have, this is where you'll write them out. So I have just 2 on the pod here, so I'm going to write knob 1, knob 2, and then for the last value that you put, you can just write number of ADC channels, because that'll be the number, since this is 0 index, so knob 1 is technically 0 behind the scenes, and this is 1, then this will be 2, which is the exact number that you have before then. And make sure to put a semicolon at the end of that. So I'm just going to make our own function down here just to keep things tidy for initializing all of our analog to digital stuff. So I'm just going to say initialize ADC, and now we can initialize everything. So I can just say ADC channel config, and then ADC channel config num of ADC channels. So now we're just declaring an ADC channel config array that is the size of the amount of channels we had, which is why that enum is so helpful. So now we can declare all of our knobs by saying ADC channel config, and then we can use our enumerator to get the index of which one we're initializing. So I can say knob 1 and init single, and then pot 1, and that's all. So then you can just go through and do that for every single one that you added. So I'm going to say knob 2 init single, pot 2. And then we have to actually tell the daisy to initialize this. So we just do that hardware variable up here, .adc.init, and then we can feed into that the ADC channel config. And I think we have to give it the number of channels, so that we can just give again that enum right there, number of channels. So perfect. Now we can just put that in the main function. So now that will all be initialized. And then we can make another function for actually processing all of that and putting it into our variables. So this is also really easy. We just take this distortion amount that I'm going to put with knob 1. So I just say distortion amount equals, and then we do that hw.adc.getFloat. GetFloat is your normalize. So this will be from 0 to 1, 0 when it's all the way on the left, 1 when it's on the right. Get will give the like raw potentiometer values, which I think will go up to like 65,000 or something, or 6,000, I forget. So I don't really know why you'd want that. You can always multiply this by whatever range you want, which we're going to do. But I just say get float, and then I'm just going to set knob 1, but then this is where you can just easily pick which knob you would like. So yeah, this is again the define up here. That's just going to be used for initializing this, but then from now on you should use this enum here, because you're telling it which channel of our config you actually want to grab that data from. And now there's a couple things we can do here. Later with the chorus, I'm going to show you this nice fmap function that comes with the Daisy SP library, but you can also just do some math. So in this case, we want, say I want it to go up to like 50, then I can times that by 50, but you have to remember that the lowest value of this is 0, and if this were being times by 0, it would obviously be silent. So then we also just want to hit +1, and it's that simple. So this will technically go to 51, so this will go from 1 to 51. Okay, one thing, yeah, I totally forgot to do is these functions are declared after I'm actually calling them. So in C++, I actually have to throw those, let's just put them here. and I have to say void. And so now it'll actually know that function. And then while we're doing that, I also totally forgot to even put the process ADC. So let's declare that up here. And then we have to actually put that in our audio callback. Not the main, because like I said, this is just runs once when you initialize the daisy or when you like plug it in. Whereas up here, this is called very, very often. So we do all of our processing in here. I also forgot that you're supposed to do the hw.adc.start after you do a init. So make sure you have that. And now we're ready to flash the daisy. So now we have a distortion with an actual controllable distortion amount. Later we'll get into how you can do non-linear mappings, because obviously right now this is just pure 0 to 1 and you might not need those super high ranges until you're at the very end. So we'll do that in a sec. You finished episode 2. That's amazing. Hopefully by now you have a small basic understanding of what DSP is and you've written a simple distortion. In the next video, we'll go over how to use the Daisy SP library so we can program some more complex stuff with it not really being much more complex at all. If you want to follow the full build, the playlist is linked below. See you there.